Greetings everyone, this is Habib Tamid Hossain along with my groupmates Salman Al Fayaz and Qazi Zubair Ahmed, and our presentation is about the thermal analysis of optimized exhaust manifold of an IC engine. Today we are going to discuss about the introduction part where we'll give you a short description on the exhaust manifold, the objectives, the problem overview, methodology on how the research work took place, outcomes of the research work, and in the conclusion part we'll summarize the overall research work. In automotive engineering, exhaust manifold collects all the exhaust gas from different multiple cylinders into one pipe. Performance of an IC engine depends on the thermal condition of exhaust manifold. Our objective is to inspect the thermal distribution at outlet section of exhaust manifold, to design an optimized exhaust manifold for an IC engine, to observe the overall heat distribution and temperature at the outlet section of exhaust manifold. When the temperature of the exhaust manifold increases excessively, many engine faults and issues develop, such as engine detonation and poor fuel economy. And now the methodology of the research will be described by Sadman Al Fayaz. Thank you.
Thank you, Habib, for the floor. Now I shall be discussing about the methodology of this project, which includes the 3D CAD modeling and the numerical analysis of the entire project. So, taking the parameters of a conventional vehicle, we have modeled three different exhaust manifolds with three different outlet diameters. That includes the 30 millimeter outlet, the 40 millimeter outlet, and the 50 millimeter outlet as well. All the designs have been conducted through SolidWorks by using necessary syntaxes. Now, in terms of the governing equations, we have set two basic equations that has been used throughout this project. Number one is the energy balance equation that basically justifies that the enthalpy of the gas which has been flowing through the walls of exhaust manifold that gets reduced due to the heat transfer to the wall. This explains that the heat transfer between the burned gas and the tubular walls are resulted from forced convection, which has been set as one of the prime boundary conditions. Now, in terms of the turbulent model equation, we are using the SSTK omega model that has been used to simulate the near wall region more accurately. As we are simulating the entire model of the exhaust manifold, it is mandatory to know the near wall region temperature. So as for the numerical analysis, before setting up the boundary conditions, we need to put these models to a mesh generator which has been meshed as fine as possible, and the number of elements which has been showing at the right side of the slide has been shown. In terms of boundary conditions, we use the SSTK omega turbulence model for the viscous flow. As for the inlet condition, mass flow inlet has been used at 0.01 kilogram per second, where the temperature is at 1500 Kelvin and the pressure is at 200,000 Pascal. For the outlet section, the pressure outlet has been set at 25,000 Pascal and the temperature is at 300 Kelvin. For the wall condition, we use the no-slip condition. As for the continuity criteria, all the criteria has been converged. For the medium of heat transfer, we use the convective heat transfer as this is the combined process of conduction and advection. Now for the remaining slides, I'm requesting my other groupmate, Mr. Qazi Zubair Ahmed, and to take the floor for the rest of the presentation. Thank you.
Thank you, Faiz, for the opportunity. Figure 5 shows the velocity control of exhaust manifold at the middle section for all the models. It has been clearly observed that the velocity has been increased at the outlet section of 30 millimeter diameter, whereas for the diameter of 40 millimeter and 50 millimeter, the velocity has been increased for a certain time and then get reduced due to the gradual expansion of the outlet diameter. In the next section, we can see that the figure 6 illustrates the contours of pressure of all the exhaust manifolds at the middle section. It has been observed that the pressure has been decreased gradually in the 30 millimeter outlet section. But in the terms of 40 millimeter and 50 millimeter outlet section, there is a change in the pressure. It starts to fall gradually where the pressure has been recovered after certain amount of pressure drop at the outlet section of 40 millimeter and 50 millimeter respectively. From the figure 7, temperature profiles of all the outlet section of exhaust manifold at the mid section. It has been found that the temperature distribution at the outlet section of 30 mm has the highest temperature profile than the 40 mm outlet section. The temperature distribution at the outlet section of 50 mm has the minimum value as seen from the figure. Therefore, with the increase of outlet diameter, the temperature gets reduced at the outlet section. Now, in this graph, the temperature curve for both the outlet section and the wall section of the exhaust manifold are shown for all the respective diameters. We can see that case 3, which is of a 50 mm outlet diameter, has the lowest temperature outcome in terms of wall temperature and outlet temperature compared to the other conducted cases. Now heading to the conclusion part, the exhaust temperature profile represents the heat fluctuation across the exhaust manifold of an internal combustion engine. Several factors affect the temperature profile, including engine running circumstance, fuel characteristic, exhaust gas recirculation, and after-treatment system. In order to increase the longevity of an engine, we carried out a study regarding the outlet section of exhaust manifold of different diameters. After going through several simulations, it has been found that with the increase of outlet diameter at the outlet section, the temperature gets decreased, which can be fruitful in terms of keeping the performance of an engine smooth. As the catalytic converter removes all the harmful emission from the engine, keeping the exhaust manifold at a reasonable lower temperature can assist the catalytic converter to emit the harmful exhaust gas effectively and will help to reduce the excessive noise and vibration as well. And that brings us to the end of our presentation. We'd like to thank you enormously for your precious time. Thank you.